Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to Chemical Reactor Design, aka Ching 323, where you're gonna learn about rates, reactors, and beyond. Okay, so we have finished already chapter 2, and today we're gonna start chapter 3. The title of chapter 3 is Rate Laws and Stoichiometry, and we're gonna divide the chapter into two parts. The first part, we're gonna learn about rate laws for irreversible reactions and reversible reactions, and we're gonna learn how to write the rate laws. And the second part, it's about stoichiometry, where we're gonna learn how to utilize stoichiometry to write concentration as a function of conversion. Okay, so we're gonna start lecture 11. In this chapter, in chapter 2, we have learned that we need some kinetic data, like the rate of reaction versus conversion, in order to design a reactor. In this chapter, we will show how to obtain the rate of reaction as a function of conversion and temperature, as opposed to having the rate of reaction versus X data in tables. This relationship between the rate of reaction and conversion will be obtained in two steps. First, we're going to define the rate law, which relates obviously the rate the rate of reaction to concentration and temperature. Then we're going to develop a stoichiometric table so that we can write concentration as a function of conversion. Then we can substitute for concentration with this equation, so we'll end up with having the rate of reaction as a function of conversion and temperature. Okay, so let's start part 1, rate laws. In fact, because you have already finished applied physical chemistry course successfully, so we're not gonna talk a lot about rate laws. We're not gonna dwell on the subject because you know it already. I'm gonna just present to you a table to summarize rate laws, the different type of rate laws. Okay, so let's have a few examples about elementary and non-elementary rate laws. Of course, you already are familiar with elementary and non-elementary reactions, but now we're gonna apply the same concept, however, on rate laws. Let's take the first example is this reaction, where we have two molecules of NO2 colliding together to produce NO3 and NO. From chemistry, we know that this reaction is elementary, and when we say elementary means ibtidai, means this reaction happens as is. So in fact, when two molecules of NO2 collide together, they form right away, directly, they form NO2 and NO molecules. So we know that this reaction is elementary. Since this reaction is elementary, the rate law would definitely be elementary. Elementary means ibtidai, simple. How is it simple? As you can see, it's very simple. It follows the power law module. So the rate of reaction is function of or equals K times the concentration of the reacting species raised to the stoichiometric coefficient. As you can see, you have 2 here and you have 2 here. So the rate law is elementary as well. Again, the power and the rate law equals the stoichiometric coefficient. Let's look at this reaction. Chemistry tells us that this reaction doesn't happen this way. In fact, it happens through another mechanism. So there are few steps that when you add these few steps together, you get this reaction. So this reaction does not proceed the way it's written. So when two molecules of NO2Cl collide together, it doesn't produce right away two molecules of NO2 and one molecule of chlorine Cl2. So this reaction is not elementary. Let's look at the rate law. It's a power law model, as you can see, concentration raised to a power, but this power, which is 1 here, is not identical to the stoichiometric coefficient. So obviously the rate law is not elementary, مو بابتدائي, not elementary, it's not simple. You cannot just simply write this rate law. Let's look at this example. Again, chemistry tells us that this reaction is not elementary. How do we know? Because it's almost impossible to have collision between two molecules of NO and one molecule of oxygen at the same time, and this collision have enough energy to produce a product. The possibility of this reaction happening this way is almost impossible, non-existent. So therefore the reaction is not elementary. Okay, let's look at the rate law. It's a power law model, and as you can see, the powers are identical to the stoichiometric coefficient. Therefore, this is the simplest rate law you can write for this equation, and therefore the rate law is elementary. So again, non-elementary reaction because you have thermomolecular reaction. You have three molecules together here, and the reaction, in this case, we say the reaction follows an elementary rate law. So we already established that the rate law is elementary, ابتدائي, and simple. Okay, and I know that the reaction is not elementary, but you can say that the reaction follows an elementary rate law. Okay, another example, CO plus Cl2. Again, the chemistry tells us this reaction is not elementary. Let's look at the rate law. It's a power law model, and the powers here, let's look at this, 1.5. The power here is not identical to the stoichiometric coefficient. So simply, the rate law is not elementary. So you have here non-elementary rate law. And obviously, you can also conclude that this reaction is not elementary, because if this reaction was elementary, the rate law would be elementary as well. But since the rate law is not elementary, then therefore this reaction for sure it's not elementary as well. Let's look at this reaction, which is a catalytic reaction. So you have a toluene reacting with hydrogen to form benzene and methane. The reaction is not elementary because obviously I'm using a catalyst. Therefore, the reaction is not directly between toluene and hydrogen. The surface of the catalyst is involved. So this is not the most elementary step in the reaction. There is a mechanism for this reaction. Okay, let's look at the rate law. The rate law looks something like this, where you have K as the rate constant. We have capital K, so that means we're talking about thermodynamics. This is the what's known as adsorption equilibrium constants. Adsorption equilibrium constant. They are equilibrium constant but related to the adsorption process. And K, as we said, is the rate law. This form of rate law is referred to as Langmuir-Hinshelwood kinetics. Okay, let's solve together this exercise. The following is a reaction that follows an elementary rate law. So this reaction is in fact not an elementary reaction, as we can guess, because it's almost impossible for this reaction to happen in one step, where you have a collision between two molecules of A and one molecule of B at the same time, where they have enough energy of collision to overcome the activation energy and then to form C. So this reaction is not elementary. However, it follows an elementary rate law. So that means the rate law is elementary. Okay, so in this reaction, A is a precious compound and used in limited quantities. The question is, the rate law is written as, this option, this option, this option, or all of the above are correct. What's your choice? Yep, you got it right. This is the correct answer because the rate law is elementary. So it has to follow a power law model. As you can see, this is a power law model where the concentrations of the involved species, of the reacting species, raised to the power. And since it's an elementary rate law, the powers are identical to the stoichiometric coefficient. So this is the correct answer only. Okay, so I assume you already know how to write rate laws for irreversible reactions, whether they are elementary or non-elementary. Okay, but of course you should be given enough information to decide on that. Let's now concentrate on writing the rate law for reversible reactions. To illustrate how to write rate laws for reversible reactions, we will use the following reaction. Benzene, two molecules of benzene is forming one molecule of diphenyl and one molecule of hydrogen. Symbolically, we can write it as 2B produces reversibly produces D plus hydrogen. And let's look at these two symbols. Here we have Kb. Obviously, this is the forward reaction rate constant. And here we have K minus B. So this is the reverse reaction rate constant. And of course, both are written based on the species B. So in this discussion, we shall consider this gas phase reaction to be elementary and reversible. As we mentioned earlier, the forward and reverse rate constants Kb and K minus B respectively are defined with respect to benzene. Benzene B is being depleted, consumed by the forward reaction, as you can see. So we can write this equation this way, and you have Kb there, in which the rate of disappearance of benzene is, obviously it would be minus Rb forward, because you have the rate of disappearance of benzene through the forward reaction. It's elementary reaction, so the rate law would be written as Kb times concentration of B raised to the power 2. Or the rate of formation of B for the forward reaction is simply written as Rb forward equals minus Kb times Jb squared. For the reverse reaction between diphenyl and hydrogen, so basically we are standing at this side and we're looking at the reverse reaction. So let's write the reverse reaction. So here we go. This is the diphenyl, this is the hydrogen reacting to form 2 molecules of benzene, and the rate constant is K minus B. Again, the rate constant is based on the species B, benzene. The rate of formation of benzene is given as, again the reaction is elementary, Rb reverse equals K minus B times the concentration of diphenyl raised to the power 1 times the concentration of hydrogen also raised to the power 1. Again we have here Rb reverse, the rate of formation of B through the reverse reaction. Again, both the rate constants Kb and K minus B are defined with respect to benzene. The net rate of formation of benzene, so now we want to calculate the net rate of formation of benzene, is the sum of the rates of formation from the forward reaction and the reverse reaction. So if I want to know in total how much benzene I'm producing, so I should sum up all the rate of formation of benzene. So let's do that. Rb, which is really actually the net rate of formation, because you have a plus here, of benzene equals the rate of formation of benzene through the forward reaction and that through the reverse reaction. So there we go. You already know that Rb forward equals minus Kb times Cb to the power 2, and Rb reverse equals K minus B times Cd times C hydrogen. Or the rate of disappearance of benzene, that is minus Rb. Simply we can multiply both sides by negative, by minus sign. There we go. Okay, let's take Kb as a common factor. Then you have here K minus B over Kb. At equilibrium, the net rate of formation of benzene, is 0. Of course, because at equilibrium, the forward rate of reaction equals the reverse rate of reaction. So in net, you are not consuming any B. In other words, you are in fact consuming B through the forward reaction at the same rate that you are producing B through the reverse reaction. Therefore, the net rate of formation of benzene is 0, or you want to say the net rate of disappearance of benzene is also 0. Okay, so if we put here 0, you can divide or cancel out the Kb, and you can take this term to the other side and then do some manipulation and you get this equation. So now you have Kb divided by K minus B equals the concentration of diphenyl at equilibrium times the concentration of hydrogen at equilibrium divided the concentration of benzene at equilibrium raised to the power 2. And of course we added E here to represent that these concentrations has to be the concentrations at equilibrium. Okay, let's look at this part. I'm sure that this part reminds you of something that you are familiar with. That is Kc. So from thermodynamics, you know that Kc is defined as the concentration of the product, right, divided by the concentration of the reactant, and each raised to the stoichiometric coefficient. So we call this Kc, or what's known as the concentration equilibrium constant. This is something you have studied in thermodynamics. Okay, if this is true, then if this side equals Kc, then this side also equals Kc. Or if you rearrange, you can say that K minus B divided by Kb equals 1 over Kc. So let's substitute this ratio with 1 over Kc. You can see this. And we get this rate law. Now I have written a rate law for an elementary reversible reaction. طيب. So this is the rate law, this is the definition of Kc that is here. Of course, we have learned that we came up with this through the steps. And now we have the following question that you should answer. Where do we get the values of the following constants? Kb, this guy, and the Kc, which is this guy. Where do we get them from? Any guess? Yes, you're right. Kb is related to kinetics, right? It's the business of kinetics. It's a rate constant, so it's related to kinetics. Okay, and this is the rate constant. For example, we can calculate it from Arrhenius equation, or we can find it from experiment. What about Kc? It belongs to the science of thermodynamics. So you get it from thermodynamics. For example, you can go to the lim K versus 1 over T figure, or you can use the definition of Kc, definition of K. So you have here K, which is function of T, is defined as exponential of minus delta G reaction. Actually the standard delta G reaction minus standard, you can see here, standard delta G reaction evaluated at the system temperature divided by RT. And here we have K's, and in fact K is the equilibrium constant, is the original equilibrium constant, which is function of temperature only. How is that true? You can see here Kc is defined as exponential of minus standard delta G reaction at temperature T divided by R over T. So the whole right hand side is function of temperature only, because regarding to delta G reaction, when you say standard, that means you have already specified the pressure, which is the standard pressure, 1 bar, and that you have already specified that these calculations are based on the properties of the pure species. And the third thing is that this reaction is carried out at the specified state. For example, you need to specify, is it the gas phase, is the reaction in the gas phase, or is it in the liquid phase or is it in the solid phase? And if we're talking about gas phase, then for it to be standard, we are basically assuming that the gases behave ideally. And at the end of the lecture, I would like to remind you to review thermodynamics, especially chapter 13 in the textbook Smith and Fennis. And if you need, maybe you can read this topic, which is the reversible reactions and how to write the rate laws. You can read more about it in the textbook or in applied physical chemistry textbook. With this, I end up today's lecture. Thank you very much and wish you all the best.